continue the discussion on flexible manufacturing systems. In the previous lecture we have seen machine loading problems, where jobs are assigned to similar machines with the objective of balancing workload. Subject to tool slot constraints. Now, the objective of balancing the workload effectively results in minimizing make span. Or minimizing the total time at which all the jobs are completed. Each machine has a tool drum with a certain capacity, and each job requires certain number of tools, and the job should be assigned to machines such that the total tools required is less than or equal to the tool handling capacity of the machine. In addition, we also saw the effect of tool saving constraints, where if two jobs assigned to the same machine require common tools, then the total number of tools required is the union set of both the tool requirement and can be less than the sum of the tool requirement in case of common tools. For example, if J1 and J2 go to M1 machine 1, if this requires 3 tools, this requires 4 tools, and if one tool is common, then it is enough to give 6 slots for these two jobs put together. We also saw that tool saving constraint can further reduce the make span. At the same time, from a modeling perspective, tool saving constraints brings in non-linearity to the problem, and even the problem of reassigning jobs to machines becomes involved and complicated if tool saving constraints are included. There is enough literature where researchers and authors have considered tool saving constraints in their solution to machine loading problems. In addition to minimizing the make span, we also said that actually we need to minimize tardiness, which means that each job has a due date and these jobs have to be scheduled such that they meet the due dates, and in the event of them not being able to meet the due date, we minimize the deviation from the due date or minimize the delay, which is called tardiness. We also mentioned that in case of large number of jobs where the total tool slot requirement is very large and tool slot availability is small, then we perform the operations in multiple batches where jobs are assigned to machines and then jobs are grouped to form batches, and such that all the jobs within a batch, the tool slot requirement is less than or equal to the tool availability on the machine. So, we also get into multiple batching problems. So, now the decision problem is, given a set of jobs, which job will go to which machine, which is the loading problem, in which batch of which machine, which is the batching problem, and in what order, which is the sequencing problem. So, the make span as well as the tardiness will depend on all three aspects to it. So, let us look at this with a very simple example to understand the effect of tool slot saving and the effect of tool slot saving on objectives such as make span and tardiness. So, we consider 3 jobs J1, J2 and J3, and we consider a single machine which is M1. So, there is no machine loading problem because all the jobs will go to machine M1. So, the processing times are 5, 7 and 7, and tool slot requirements are so tool slot requirement is 3, 4 and 4, and tool slot availability is 6. The due dates are 12, 18 and 10. Now, let us look at this issue. Now, there are 3 jobs, there is a single machine, the tool slot requirements are 3, 4 and 4. So, we can assign only one job at a time, because if we assign 1 and 2, the requirement is 7 against capacity of 6. Similarly, if we assign 2 and 3, the requirement is 8 against capacity of 6, and 1 and 3 also the requirement is 7. So, at present we are not considering tool slot saving constraints. So, we will be able to do only one job at a time, and we need 3 batches, each batch having one particular job. Now, we have also said that changeover is 3 time units. Changeover is 3 time units. Now, the due dates are 12, 10 and 18. So, if we arrange them based on earliest due date, then we will do J3 first, then we will do J1 and then we will do J2. Now, J3 will be over at time equal to 7, because it takes 7 units of time. 4 tools are inserted into the tool drum having 6 tool slots. Now, once J3 is over, we have to change the tools to do J1. So, that is going to take plus 3 units of changeover, and then we process J1. So, 3 slots, 3 tools are put in. So, we have another 5 units here. So, J3 finishes at time 7, J1 finishes at time 15, and then between J1 and J2 there is a changeover. So, plus another 3, 18, and J2 requires another 7 time units. So, 18 plus 7, 25. So, these are the completion times. Now, the due dates are 12, 18 and 25. Seven, 12, 18 and 25. So, now this is tardy. So, tardiness will be 0, 0, sorry, tardiness will be, the due dates are, due date for J3 is 10, due date for J1 is 12 and due date for J2 is 18. So, we will have so now tardiness will be, this is ahead of the due date. So, tardiness is 0, tardiness, this is after the due date. So, tardiness is 3 and tardiness is 7. So, total tardiness is 10. If we ignore this changeover times, if we do not have any changeover time, then the completion times will be 7, 7 plus 5 12, 12 plus 7 19 will be the completion times. The due dates are 10, 12 and 18. So, this is the only one with tardiness, total tardiness is equal to 1. But if we include the changeover time, the total tardiness is 10. Now, if we consider tool slot saving, and if we say that jobs 1 and 2 are combined, we can save 1 tool slot. So, we can save 1 tool slot by combining J1 and J2. Now, what we can do is, since we can save 1 tool slot by combining J1 and J2, we now combine J1 and J2, and together when we combine, we require 3 plus 4 minus 1, 6 tool slots. So, it is enough to run 2 batches. So, first batch will be J3 and the next batch will be J1 plus J2. Now, we start J3 at time equal to 7, J3 finishes at time equal to 7. Now, there is a single changeover plus 3. So, this is 7. There is a single changeover plus 3. Now, J1 and J2 together are going to be done in the second batch, which means the tools for J1 and J2 are going to be put into the tool drum together, and between J1 and J2 the order of due date is J1 is done first and then J2. So, 7 plus 3 10 plus 7 17 plus 5 plus 7. Now, the tool drum has the tools for J1 and J2. There is no changeover between J1 and J2. So, between the two jobs J1 and J2, we again arrange them based on earliest due date, do J1 first and then J2. So, J1 comes first, finishes the processing, it leaves at time 10 plus 5 15, and then J2 is immediately taken up. So, it takes another 7 units, at 22 units J2 is completed. So, these are the completion times, and these the due dates are for J3 due date is 10, 12 and 18. So, this completes ahead of the due date. Here the tardiness is 3, here the tardiness is 4. So, total tardiness is 7. Now, we are able to save those 3 time units, which happens to be this changeover of 3. By reducing the number of batches, we have reduced one changeover, which is 3 units, and we are able to save this because this changeover which we had earlier is removed. So, plus 3 7 would have become 10 here. So, we save 3 units here. So, total tardiness is this. If there is no changeover time, then the completion times again will become 7 plus 5 12 plus 7 19. There is no effect of this. The due dates are 10, 12 and 18. Tardiness is 1. Only when there is a changeover, the batching problem becomes significant, or the problem of assigning jobs to batches becomes significant only if there is a positive changeover time. So, we can now see the effect of tool slot saving, particularly the effect of tool slot saving. We can see the effect of batching and we can see the effect of tardiness through a simple example as to how tool slot saving helps in reducing or minimizing the tardiness, particularly in the context of multiple batches. It is not uncommon to have multiple batches because these machines are quite expensive and we will not have too many of these machines. There could be 1 or 2 or 3 machines in a group, while the jobs that require them will be very large because they are special purpose machines capable of doing a variety of operations precisely and very well. Demand on these machines will be very high. So, the number of jobs that we will be doing will be much more and they will require a large number of tools, and then the batching problem will also come into play. In fact, the number of individual tools can also become a constraint at some point. So, we do have, it is not only enough to look at a machine loading problem to balance workload, we should also look at a batching problem to assign jobs to different batches on the machine, and then we should incorporate the changeover time, and then we should exploit the tool changeover and then build a sequence such that the final objective of minimizing tardiness is achieved. Now, all these are shown through a very simple numerical illustration here, but then the optimization problem becomes extremely complex because of the nature of decision variables. Now, we have decision variables of the type x I j k, where job I goes to machine j in the kth batch, and then within that there will be a t I j k or c I j k, which will be the completion time, or s I j k, which will be the start time. So, the optimization problem becomes complex, and as mentioned, the moment we bring in the tool slot saving constraint, the non-linearity creeps in and it becomes very difficult to solve as an integer programming problem or a binary IP, because it is non-linear. So, it becomes a binary non-linear IP. Linearizing this non-linear is possible, but not easy. So, we have to add more constraints to solve it. So, the only way we could look at solving this problem optimally is by trying a kind of a branch and bound algorithm. But if the objective is to minimize tardiness, it also becomes difficult because branch and bound algorithms, though they exist for the purpose of minimizing tardiness, they have been approached with very minimal success in terms of number of jobs that they are capable of handling, because lower bounds for tardiness are not very tight. So, this problem is indeed a very complex problem. If we increase the number of jobs, if we increase the number of machines, and also if we include the tool slot constraints. There are other simple observations such that if the tool slot constraint is very loose, in the sense that the tool slot capacity is large, then the problem, the branch and bound algorithms take lesser time, and if the tool slot constraints are tight, then the branch and bound algorithm takes more time, which means the moment the effect of tool slot saving has an impact on the solution, it takes a lot more time to solve. So, this is how we understand the effect of all of these, particularly on the batching, loading, scheduling problem, to minimize the make span as well as to minimize tardiness. Now, let us look at one more problem, which is considering different tools for each machine. Now, let us look at this through another example. considering different tools for the machines. So, here we assume that the number of tools or tools required are different for different machines. For example, if there are two machines M1 and M2, we assume for a moment that the tools are not interchangeable, which means M1 has its own set of tools and M2 has its own set of tools. Now, this is also a practical issue as well as a practical constraint, because sometimes when organizations build flexible manufacturing systems, they buy machines from the same make. Now, when they buy similar machines of the same make, then the tools are interchangeable. But if there are two machines, each is of a different make from a different manufacturer, then the tools are not interchangeable. In such instances, it becomes a little more difficult because the programs also have to be compatible with each other. Each machine will work on its own programs developed. So, it could be a slight advantage to have machines from the same manufacturer because of substitutability of tools, because of good control over the programs. Sometimes cost considerations force organizations to buy machines from different manufacturers. Therefore, each machine will have its own set of tools. Also, the processing time will be different on each machine. This assumption was there even for the earlier problem, because the loading problem without tool is like a make-span minimization on non-identical parallel processors. Now, we formulate this problem for two machines. Now, let us look at this problem as such. Now, this is the problem that we are going to solve. We will do the formulation for this particular example. So, let us assume that machine 1 has tools A1 to A5 and machine 2 has tools B1 to B5. Now, there are 7 jobs. The processing times are given in the table on two machines. Now, M1 has 4 tool slots, M2 has 4 tool slots. Now, let us explain this A1, A2, B1, B3, etc. So, if J1, job J1 or job 1 is assigned to machine 1, then we have to assign 2 tools A1 and A2 to machine 1. If job 1 goes to machine 2, then 2 tools B1 and B3 will have to go to machine 2. So, that is the way we describe. If job 5 is assigned to machine 1, then machine 1 would require tools A3, A4 and A5. It requires 3 tools. Obviously, there is a tool saving slot constraint, because if J1 and J2 are both assigned to M1, then it is enough to have only 2 tools A1 and A2. The difference here between this example and the earlier example is, here we are specifying the tools. We number the tools, each tool has a unique identity. In the earlier example, we said it requires a certain number of tools and some number of tools can be shared. So, we bring in one more level of detail into this problem. Now, we want to balance the workload. So, we will now say that let Z ij equal to 1 if job I goes to machine J. Goes to machine J. X I equal to 1 if tool I is chosen, or x k equal to 1, you could use any notation. So, here I am using a notation x k equal to 1 if tool k is chosen for M1 and y k equal to 1 if tool k is chosen for M2. So, we have the first constraint that each job is assigned to only one machine. So, sigma Zij j equal to 1 to m machines is equal to 1 for every I. For every job, each job is assigned to only one machine. Now, sigma x k is less than or equal to t, in this case 4, where a maximum of 4 tools can go to machine 1. Similarly, sigma y k is less than or equal to 4 because machine 2 also has a capacity of 4. Now, Z11, if job 1 is assigned to machine 1, then from this table we understand that x1 and x2 should both be there. So, Z11 should be less than or equal to x1 and Z11 should be less than or equal to x2. For example, I cannot have a situation where x2 is 0, which means tool A2 is not assigned to machine 1. If that happens, then Z11 I cannot assign. I cannot assign job 1 to machine 1. Now, once we write these two, the rest of them are obvious. So, this will give us Z12 is less than or equal to y1, Z12 is less than or equal to y3, because tools B1 and B3 are required if we have to do job 1 on machine 2. So, we have one constraint for each of these tools that we have there. So, we are going to have 2 plus 1 3, 5, 7, 10, 12, 14 such constraints, considering all the allocations. For example, the next one will be Z21 is less than or equal to x2 and Z22 is less than or equal to y4. Like this, we have 14 constraints for the first machine and another 14 constraints for the second machine, because you have 2 plus 1 3, 5, 7, 9, 10, 12, 2, 3, 5, 7, 9, 10, 12 constraints for machine 2 and 14 constraints for machine 1, 2, 3, 5, 7, 10, 14 for machine 1 and 12 for machine 2. Of course, xk, yk, zij are all binary. Now, we could either balance the workload or we could minimize the total sum of processing. So, we would go back and do minimize Pij Zij. Now, this would minimize the total time of processing, sum of the times of processing on both the machines. We can also balance the workload by minimizing the maximum of the loads by defining the maximum of the load as u and u greater than or equal to Pij Xij for all j. So, we can do that. So, this is the formulation. The nice thing about this formulation is that the tool slot saving constraint becomes implicit. It is not nonlinear, but it takes care of the tool slot saving constraint. If we see carefully, it is not nonlinear, but as I said, if we assign jobs 1 and 2 to machine 1, we would actually be utilizing only 2 slots and not 3, because job 1 on machine 1 would require tools 1 and 2, A1 and A2. Job 2 on machine 1 requires only A2. So, you could assign both of them to machine 1 by simply fixing tools A1 and A2. So, tool slot saving constraint is taken care of the moment we name the tools and say these are the tools that are required. Only when we do not name the tool, we get into nonlinearity coming in when we define the saving as so much is saved if these two are put together. So, the problem continues to be linear, and we solve this problem to get the binary integer has x2, x3, x4, x5 equal to 1. So, it has x2, x3 equal to 1, y1, y2, y3, y5 equal to 1, and it has z12, z21, z32, z12, z21, z32, 41, 51, 61, 72, 41, 51, 61, 72 equal to 1. So, now let us look at this solution. Now, from this solution we assign, this is M1, this is M2, this is jobs. So, let us go back to this. Job 1 goes to machine 2. So, job 1 goes to machine 2, job 2 goes to machine 1, job 3 goes to machine 2, job 4 goes to machine 1, job 5 goes to machine 1, job 6 goes to machine 1, and job 7 goes to machine 2. Now, from this x2, x3, x4, x5 means tools A2, A3, A4 and A5 go here, y1, y2, y3, y5, B1, B2, B3 and B5. So, if we look at J1 goes to M2, it requires B1 and B3, B1 and B3 are here. J2 goes to M1, it requires A2, A2 is here. J3 goes to M2, it requires B2 and B5, they are here. J4, A2 and A4 are here. J5, A3, A4, A5 are here. For J6, it is A4, A5 they are here, and for J7, B1, B2 are here. So, all the 4 tool slots are utilized, but we have enough tools to carry out all these jobs. Now, the times are, for M1 it is J2 which is 4, J4 which is another 8, J5 is 6 and J6 is 7. So, this is equal to 12, 18 plus 7, 25, 1, 3 and 7, 2 plus 5, 7 is 7, 14. So, the loads are 25 and 14 with the total equal to 39, total equal to 39. We could solve another problem to balance the workloads. We may get a slightly different solution also, but the total would be 39 or more in such a case. Now, if we wish to balance, then we would minimize u greater than or equal to Pij Xij for both the machines, and then we will be able to balance the workload on that. We could use any of these objectives, but here we are not looking at tardiness. We are not right now, we have not defined due dates for these jobs, and then we have not defined tardiness. And if we define tardiness, then we get into difficulty, and as I mentioned, the decision variables will be based on time of completion. Right now it is only an allocation problem, so the decision variables only represent the allocation of jobs and tools to various machines. Moment we bring in due dates and tardiness, the problem becomes a little more complicated. It continues to be linear because we have the tool slot saving constraint, as I mentioned, is not nonlinear in this case. Nevertheless, the problem becomes involved and is hard because of the binary nature of the variables. Now, all these variables are 0, 1 variables. Because of the binary nature of the variables, the problem becomes hard. So, we could think in terms of some heuristics. Now, let us look at this. Based on minimum processing time, we could think in terms of a heuristic like this. So, let us start assigning them. So, M1, M2. Based on minimum processing time, let us start assigning. So, M1 goes to J1 goes to M1. So, along with J1, tools A1, A2 go here. J2 also goes to M1, tools are already available. J3 goes to M2, so tools are B2 and B5. J4 goes to M2, B3 and B4. So, all the 4 tools are exhausted, tool slots are exhausted. J5 on M1, A3, A4, A5 cannot include. Therefore, J5's B2, B3 are already here. So, J5 goes here. J6, A4, A5. So, we could look at J6 and A4, A5. J7 goes to B2, B1, B2 we do not have, but A3, A5 also we do not have, because J7 requires A3 and A5. So, we are not able to allocate J7. So, let us see what happens here. So, we change this. Now, in this way we are unable to allocate. So, let us follow or slightly modify this heuristic to see what we do. So, we allocate J1 to M1. So, we allocate J1 to M1, tools A1 and A2 go to M1. J2 also goes to M1 because the tool is already available and minimum processing time. So, J1 and J2 go here. Now, we look at J3. J3 goes to M2 based on minimum processing time. So, J3 comes here and tools B2 and B5 come here. Now, J4 goes to M2 and B4 is added. So, J4 goes to M2, tool B4 is added because it requires no. The heuristic says J5 goes to J5 is allotted to M2 and B3 is also allotted to M2. So, J5 is allotted to M2. So, J4 goes this. Now, J5 also, J5 cannot be put on M1 because J5 requires tools A3, A4 and A5. So, we will exceed this. So, J5 has to come here. So, J5 requires tools B2 and B3. So, B3 is added. Now, J6 requires B4, but based on minimum processing time J6 has to go to M1. So, now we have a conflict because J6 requires A4 and A5. So, we have enough slot to give A4 and A5 here and put J6 on the minimum load machine, but we know that if we do that we cannot accommodate J7. So, we have to accommodate J7. So, we follow the other rule by saying that if the full set of tools are already there on one machine, do not go by minimum rule, assign it there, and then if it is not, if you have to add something, then go to the minimum rule. So, by that condition J6 will come here because B4, which is the machine that it requires, has B4 is available here. So, now for J7 we need A3 and A5. So, we put J7 here, we need A3 and A5. Now, J7 should ideally go to M2 and requires B1 and B2. B1 and B2 are not here and we cannot add. So, we look at the other one. So, it requires A3 and A5. So, I put it here, I add A3 and A5. Now, what is the workload on this? The workload is 1, 2 and 7 for M1, 1 plus 4, 5 plus 9, 14, 2, 3, 4, 5 and 6, 5 plus 7, 12 plus 8, 20 plus 8, 28, 5 plus 7 plus 8 plus 8, 28. So, this heuristic algorithm gives us a solution like this, but this heuristic algorithm is based on some thumb rules that if we pick a job and if all the tools required to do that job are already assigned to a particular machine, then we do not go by the minimum processing time rule, we assign the job to that machine. But if all the tools are not there on a particular machine and some tools have to be added, then we go by the least processing time and see if we can add the tools and put it there if there is enough space. Otherwise, we go to the next least processing time and we keep proceeding using this algorithm till we are able to allocate all the jobs. So, this is how we carry out the loading of jobs on machines with specific tools required and tool slot capabilities on each of these machines. We have not addressed the batching problem here, nor have we addressed the tardiness and scheduling problem here. We took a problem where with 4 tools we are able to allocate all of them. If we had more jobs, say we had 15 jobs or 10 jobs, then we will not be able to do it with tool slot capacity of 4. So, it would require multiple batches. In such case, what we will do is, we will temporarily leave out the tool constraint, we will simply solve For example, if instead of these 7 jobs, if we had 10 jobs that have to be allocated to these 2 machines, each of these 10 jobs has a specific set of tool requirement like A1, A2, etc. So, now we know for sure that we will require multiple batches to operate on this. So, phase 1 problem will be to simply balance workload without considering tool slots. So, this problem will be similar to non-identical parallel processor make span minimization on a single machine, because each job will require different processing times on the machines. So, parallel processors are non-identical. Now, tool slots are not considered. Then for example, if we have a solution which says jobs J1 to J5 will go to M1 and let us say jobs J6 to J10 will go to M2. Suppose this is the solution. Then we have to solve this problem only considering tools such that we now define them into batches, and then we say that out of these 1 to 5 we may consider 2 batches or 3 batches, and then say this job will go in this batch. And then if a set of jobs go into this batch, then the union set of tools should be, we should be able to accommodate the union set of tools into the tool slot. So, the processing time does not come into the picture, we simply maximize the number of jobs that can go to the first batch. So, maximize number of jobs that go to the first batch such that the tool constraint is satisfied. Similarly, maximize the number of jobs that go to the second batch such that the tool constraint is satisfied. Then remove those jobs, and then from the remaining jobs solve this problem again to maximize the number of jobs that go to the second batch, and so on. Or we can combine the batches and solve such that we maximize the total number of jobs that go to the first batch, second batch, third batch, and so on. We can actually combine all of them and bring them into one large optimization problem, where we can combine the batching problem, maximize the number of jobs that can be done on each batch. Then we get into the issue of scheduling if each of these jobs has a due date. Sometimes we put a due date constraint, the due date will force a particular job to go into the first batch because of due date considerations. In such cases, we can either define completion time for each job and do it, or if that is a little difficult, we can define completion time at an aggregate level. For example, if in this 3 we divide them into 2 batches, and if let us say J1 to J3 go to the first batch, J4, J5 go to the second batch. Now, the sum of the time when this batch is completed, the sum is the processing time of J1 plus J2 plus J3. Now, we may make an assumption that all the jobs actually come out at the same time and not immediately after they are processed. If so, then the sum of these should be within the due date. The only difficulty there is in practice, if all 3 go in one batch, depending on the sequence, they can actually come out sooner than the batch is completed. The jobs within a batch, they do not come out at the same time. The jobs they come out as and when the processing is over. Only the tools are available for a change after the entire batch is completed. So, if we really want to minimize the tardiness, then we have to define the variables in terms of completion time of the job on that machine. So, it becomes a fairly complicated problem that involves loading, it involves batching, it also involves scheduling and sequencing. The nice thing about this formulation is that it does not explicitly have the non-linearity component which the earlier formulation had, and this is also practical in the sense that the machines could be of different makes, and therefore they could have different types of tools that go in, and the tools are now numbered and named, saying if this job is to be done, then these specific tools are required. Further models on flexible manufacturing we will see in the next lecture.